All right, hello everyone. Today we're going to finish off going through electrolysis by having a look at Faraday's laws. So some practice questions here. So this is largely to do with basically having quantitative values for electrolysis. All right. So the main point at which Faraday's laws come up is in electroplating. So electrolysis we can use to make different things. A lot of the time it comes up in electroplating. We'll see some examples where it doesn't in a minute, but this is one that you'll see a lot, where basically we're using electrolysis to cover a certain metallic object with some kind of other metal. So it doesn't need to be conductive, so it's normally a metal covering another metal. And normally we basically take a cheap, solid, strong inside material and we cover it with something that looks nicer, but is it's less reactive with air, but is also generally more expensive. So we can gold plate something else so it looks like gold, but we don't actually have to pay the price of making something that's solid gold. So how this normally works is that basically you get a power source and you connect the metal that you want to plate your object with, and you take the object itself and you just dunk them into the same bigger container, whatever you want. So whatever's going to be plated acts as the cathode, because reduction happens there, which will plate the metal onto there. And at the other end, the other metal will basically dissolve into the solution. And generally, as part of this process, the electrolyte is made up of the same metal as the anode there, so that the anode will continually replenish the electrolyte as it's plated onto the cathode there. So how we actually use maths here, basically there's a few new terms that you do need to know in terms of electrolysis here. So the first one is that you need to know about Q. So Q is kind of like the mole. It's basically a measure of the amount of charge in an area, which basically because each electron has the same charge, it basically is kind of like an amount of electrons. It's kind of more of a physics term, but it has a specific meaning for voltage and current, the way we measure them, so volts and amps. So we kind of need to convert backwards and forwards between Q and our actual number of electrons. So Q is charge, and the unit is a coulomb, which is this capital C. Next is the current. So current is basically how many electrons are going past a certain point in the circuit. You can also say it's the number of coulombs per second is the actual official unit, which is also known as an amp, which is A. So now the letter for this is I, which is due to basically some French word. So I is referring to current. Current is not C. C is coulomb, the unit for charge. But that's another one of our electricity measurements there. And so these two are variables. These two can be different things. The third one we've got here is Faraday's constant, which is always 96,500. So it's kind of like Avogadro's number in the sense that you can always just chuck this into calculation. It's always going to be the same thing. Faraday's constant is constant, as the name suggests. So it's always going to be that 96,500. And that's going to let us convert between charge, so Q, number of coulombs, and our number of electrons. All of our current values are measured using coulombs. All of our chemistry values are measured using number of electrons. So we need to be able to go from one to the other. And you get a bit of this information in the data book. You get this first equation here. So the charge is equal to the current times time, which makes sense because the current is how many coulombs are going past per second. And the number of moles of electrons is equal to charge divided by Faraday's constant. If you want to, you can mentally just replace this by number of electrons equals Q divided by 96,500. The fact that Faraday's constant is 96,500 is also just lower down on this page, which I think is page 5 or 6 or something like that of your data book. So you don't need to go and memorize that or anything like that. So you can already see kind of like a working pathway that we can use along here. So basically, if we have the current and time, we can calculate Q. And if we have Q, because we always know what F is, we can always find the amount of electrons. And that's basically the first step of running a calculation normally. So I've basically put the list of conversions we can go here. It's basically a linear sequence of calculations we can do. If we have current and time, we can find charge. If we have charge, we can always find amount of electrons. If we know what metal we're working with, we can always find the amount of that metal from the amount of electrons. And then from the amount of metal, we can always find the mass of metal using our mass equals amount times molar mass equation. Now this case, I put exchangeable arrows here, or reversible arrows here, because we can go either way. We could be given a mass value and convert that into an amount of the metal, and then an amount of electrons, a charge, and then a current. That would work as well. So this is exactly what I just said here, but basically we're going to do something like this. We just kind of need to identify where we're starting in this linear sequence, and we need to figure out where we're going. So we're not necessarily always going to start at one end and go to the other one end. So you might be given the charge and then have to find the amount of the metal, for example. Or you might be given the mass and have to find out the amount of electrons that we could be going through the circuit. And that's about it. So there are a few new equations, but they're not particularly complicated. It's kind of just adding them onto your repertoire of things that you know how to use. So let's start with one here. So we've got an electroplating cell, and take a look at our information. We've got a lead electrode, okay, as electrode Z, so that's our anode, and we're getting some lead plated. Oh, sorry, other way around. So this is going to be the cathode because we're getting lead deposited onto electrode Z. The platinum's just not going to react. So you can't. So that does mean that the lead will run out over time. If you wanted to keep electroplating stuff, you would just make this a lead electrode. All right, so we've got 1.0 molar lead nitrate. All right, it runs for, it says a set time and current. So we don't know the current or the times. So there's no way that we can figure out the charge. And we're going to get 1 gram of lead deposited onto electrode Z. We set up some other cells, each have the same anode, but they have a different electrode Z and electroplating solution that match up together here. They operate for the same time and at the same current. All right, so the only difference between each of these chemicals is going to be basically the charge on the metal. So one thing I didn't explicitly say on the previous slide was we could normally calculate our charge using Q equals I times T. We calculate our amount of electrons using amount of electrons equals Q divided by 96,500. And then we can just use the mole ratio, looking at our half equation, to figure out the amount of metal versus the amount of electrons. So for example, in this case here, let's having a look at our thing back here. We've got a mass of metal deposited, and we're going to have to compare different metals. So we can't run it all the way back to here, and to be fair, we're not actually going to need to. But what we can do is convert our mass back to an amount, and our amount to a number of electrons. We know that the amount of electrons is going to be the same for all of them, and so then we can go back forward again, and we can test what the final mass will be for the different ones. All right. So we've got, let's start here. So we want our amount of lead is going to be equal to our mass of lead divided by our molar mass of lead. So let me quickly pull up the data book here. Let's get that open. And we've got that. There we go. So lead is 207.2. Oh, my thing went away because I stopped sharing. But basically, we've got the amount is going to be equal to our mass, which is 1, and our molar mass, which was 207.2, right? Yep. 207.1 divided by 207.2 is going to be 0.0048. I'll keep the number in my calculator. Mole there. Our half equation for this is lead plus 2 electrons goes to lead. If you're not, you should be able to figure this out just straight from the charge. So all of the metals are literally just going to be, because they are metals, It's more complicated if you've got things with oxygen floating around. Because these are just going between the ion and the metal, it's just going to be the ion plus whatever the charge on the metal is, number of electrons, goes to the metal. So I know the charge on this is 2 because there's 2 nitrates per lead here. So it's going to be lead 2 plus, and then we need 2 electrons to balance out the charges to become lead metal on the other side. So therefore, the amount of electrons is going to be the amount of lead. And using our stoichiometry, we can see that the amount of electrons will always be twice that of the number of lead. So every lead that is reacting, 2 electrons are reacting. So it's going to be twice our value from before, which, oops, is going to be 0.00, we've got a 5 here, so I'll leave that in. 0.00965 mole. All right, so that's how many electrons we have. And we should be able to basically go back again. So we've gone back to find our amount of electrons. We should be able to go to the amount of metal and then mass of metal for each one of the remaining metals. All right, so let's do chromium first. So we can see that chromium's 3. I'm going to do this in one hit just to make it a bit faster. But the mass of chromium is going to be the amount of electrons. I'm basically doing 2 steps here. Because the charge is 3, I'll have to divide this by 3. And then I'll take that and I'll multiply it by the molar mass of chromium. The molar mass of chromium is 52. And that's going to be, so I'll take my answer, I will divide it by 3 and multiply it by 52. And it's going to be 0.167 grams. So that's definitely not more metal. Now that kind of makes sense because chromium's, if we think about it, lead is really heavy, right? Lead is, lead's about 200 grams per mole, and it has a lower charge here. So chromium's, there's going to be a lower mole of chromium because it has, it needs 3 electrons per chromium and it's way lighter. So there's really wasn't any chance there. Now I'll go through the maths here, but at this stage, we can probably look at the molar mass and kind of have a bit more of a guess here. So we've got silver's 107.9, gold is here, and tin is over here. So these would be much more likely than chromium. Now silver is only 1 charge, so it means for every electron we'll get, every mole of electrons will get 1 mole of silver. So silver's looking pretty good right now. So let's just keep running through. You could do this to, for example, save some time. But obviously there's nothing wrong with just running the calculation a few different times. Now the mass of silver is going to be the amount of electrons. Now remember, for the half equation here, it's just going to be silver 1 plus 1 electron goes to silver because we know that the charge on silver is 1. If you didn't know that, it is a useful thing to know, but also we can see that it's only, there's 1 silver per nitrate in our ratio here. So I'm not actually going to need to divide it all because it's 1 silver per electron. But I will multiply it by the mass, which I think is 107.9. Yep. 107.9, which is going to be 107.9, which is going to be 1.042 grams. So that's looking like it's the correct one there. Now the gold is going to be 3 plus. If we look at that, the tin and the gold are going to be pretty similar. I'll run through them. You could just stop here, given that it was a bit higher. Maybe you want to double check it just because this is still pretty close. So the mass of gold is going to be equal to the amount of electrons divided by 3 times the molar mass of gold, which is 197. That's going to be 197 divided by 3. That's going to be 0.634 grams, which is definitely lower. and tin is going to be mass of tin equals amount of electrons divided by 2 times, what's a mass of tin? 118.7. Which is going to be 18.7 divided by 2, which is going to be 0.573 grams. So we can see the fact that the silver has that 1-to-1 ratio, whereas all of the others need at least 2 electrons, is what makes it a higher mass than the lead, even though its molar mass is actually much lower than lead. That's a lot of work for a multiple choice question. This is definitely one of the weightier multiple choice ones I've seen, just because you kind of have to do it by trial error and error at this point. All right, keep going. All right, we have an energy company investigating the feasibility of supplying energy while reducing greenhouse gas emissions. Solar panels collect energy from the sun during daylight hours, and this energy is used to electrolyze water to produce oxygen gas and hydrogen gas. And the gases are stored separately and then used in a fuel cell. So we've got 2 separate things going on here. We've effectively got an electrolytic cell here, and we've got a fuel cell down here. So this looks like a hot mess, but really it's just 2 separate things. If we think about them separately, then we'll be fine. The solar panel also adds to the clutter here, but really you could just say that this is power source. I didn't think about which one's positive and negative, so don't comment me telling me that I did it wrong. Basically, we can ignore the solar panel, just say, yeah, okay, there's some electricity coming from somewhere. All right. So I'll ignore that. But basically, we can break it down here. Just think about one at a time, because even though they like to put intimidating looking cells here, you should know about this fuel cell. They say it's alkaline on the next page. And this one here isn't particularly complex. It's just a standard cell here, and it happens to make oxygen and hydrogen. All right, so state the polarity of electrode W in the electrolysis cell. So we're only looking at the electrolysis cell. So this stuff can all go away. Don't need that. So you might look at this and go, well, I've got no information about the charges or anything like that. The information that you do have, though, is what it's connected to. So if we look around here, electrode W is connected to the hydrogen storage tank. Presumably, this doesn't let the oxygen and hydrogen through to the other side, so because otherwise it would be pointless. So it's reacting, and it's forming hydrogen there. Okay. So if we're reacting to form hydrogen, then and this is one where I think it's a bit easier if you actually just look at the next bit of the question. The question tells you, sorry, that one's an alkaline one. It's just water. Basically, we're gonna have water, and how do you get water? How do you get hydrogen from water? Now, even without looking at the electrochemical series, to be fair, we can just go, well, our water is turning into hydrogen gas. Hydrogen gas has an oxidation number of 0. Hydrogen in the water has an oxidation number of +1. So the hydrogen must be being reduced. And if it's been reduced, then it's at the cathode. An electrolytic cell has a cathode that is negative. So therefore, this one's negative here. So hopefully you followed along there. That's kind of just the theory from the previous PowerPoint. The fuel cell operates in an alkaline environment. What's the half equation for the reaction that takes place at electrode Y? So this one's electrode Y. Now it says it's an alkaline fuel cell, which means that because we're using hydrogen, which is basically the one that we see all the time with fuel cells, we're looking for the ones that have oxygen and hydrogen. So one will have oxygen, one will have hydrogen, and they've got the OHs there. So you might see some other ones, for example, this one around that has H+. That wouldn't work because there's no, well, this one's for peroxide. But basically, we're not looking for anything with H+, like that one, for example, because it's alkaline. If it was alkaline, it would react with any of the H+ and make it go away anyway. So we're looking for the 2 ones that have hydroxide. So these 2 hydroxides here. So we can see that the water is being reduced to hydrogen, which is what we said for the first part. and we'll end up with the hydroxide being oxidized to water and oxygen at the other end. Sorry, we didn't say that for this one. It's just very similar. So electrode Y, we've got oxygen. We've got hydrogen coming in at one end and oxygen at the other end. We know the hydrogen is what's going to be oxidized, so the oxygen must be being reduced, which is also the only half equation that's in. So this one here must be the right half equation. I have added this on. You had to look that up you have to actually look at the electrochemical series in the data book. So I'd write this, and I'd put states in there, but I'm being kind of lazy at the moment. There you go. There you go. So there's our half equation there. All right. So each of the 4 solar panels produces an average current of 5.2 amps and operates over an 8-hour period. Okay. So we've got some values here. We've got time is equal to, now we do want to use time in seconds because current is how many coulombs go past per second. So we're going to go 8 times 3600, which is the amount of seconds that are in an hour. If you want, you can just write that out as 60 times 60. So we're going to get 8 times 60 times 60 is 28,800 seconds. And our current is, this is a little bit of a trick question. There's 4 solar panels, each making 5.20 amps. So overall, they're making 20.8 amps. All right. So we've got some information here. We've got the current and we've got the time. Looking back here, we can see we've got current and time. We'll be able to find charge. Then we'll be able to find the amount of electrons. Then we'll be able to find the amount, which is what we've been asked for. All right, so we have our equation, Q equals IT, which is going to equal 28,800 times 20.8, which is going to equal 599,040 coulombs. That's a lot of coulombs. And then we can say number of electrons is going to be equal to Q divided by F, which is going to be 599,040 divided by 96,500, which is equal to 6.208 mole. Okay. So now we just need to convert our number of electrons to our amount of hydrogen. Now, we said before we're looking for the one that has water, and the water is reacting to form hydrogen gas. We've got 2 waters being reduced to 1 hydrogen and 2 hydroxides. 2 waters going to hydrogen plus 2 hydroxide. To balance the electrons out, we'll add 2 electrons on this side. If you use the acidic environment one, that's fine as well. They both work just as well as each other. So we see that the amount of hydrogen will be equal to half the amount of electrons that we have there. So amount of hydrogens will equal, let's put that in there, 6.208 there will equal 6.208 divided by 2, which is going to equal 3.104 mole. I don't know why I'm trying to do maths with letters. All right, 3.104 mole of hydrogen there, and there we go. That's our answer. Now we've got some different numbers here. it says this as an 8-hour period because this 8-hour period isn't measured. So it's like if I said, if I drove a car at 60 kilometers per hour for 5 hours, how far would I go? Because we haven't actually measured that and it's a hypothetical, then we don't need to incorporate error into it. So we don't need to use sig figs for that. However, this is measured. That's why there's an extra 0 on the end. So we'll use 3 significant figures, 3.10 mole there. All right. And we want to determine the pressure this amount of H2 gas would exert at SLC in a 10-liter tank there. All right. So we should be able to use PV equals nRT. Now it is SLC, so we could find the volume it would take up. Let's just use this here though, because we're trying to find pressure. So we don't know pressure. Pressure is going to equal nRT divided by volume, which is going to equal 3.10 times 8.314. Look it up in your data book. Times we're doing 25 degrees, so that's 298.15 degrees Kelvin, and we're dividing by the volume, which is 10 liters. Basically, just plug all that in there. I should be doing a capital P, and we have 3.10 times 8.314 times 298.15 divided by 10, and we get a pressure of 768.4 kilopascals. We've got 3 significant figures here, so our final will still be to 3 significant figures. 368 kilopascals there. All right. We've got another one here. So electrolysis of carbon dioxide gas in water to make ethanol. We've got 2 half equations down here, and we've got our cell here. So carbon dioxide has been blown in and it's reacting. Carbon dioxide is reacting with water to make the ethanol and some hydroxide, and the hydroxide is being oxidized at the other end to make oxygen gas and water. All right, a current of 2.7 amps is passed through the cell. The cell has an efficiency of 58%. What's the time taken for this cell to consume X mole of carbon dioxide? So the efficiency is 58%. So we can kind of incorporate that anywhere, but I'm just going to go straight away and say the actual current or effective current, I could say, is going to be 2.7 times 0.58. 0.58, which is going to equal 1.566 amps. That shouldn't be an A, that should be an I. So the actual current is basically that. Now we've been given the amount in mole. So let's look back at our pattern here. If we have the amount in mole, we should be able to find the amount of electrons, therefore find the amount of charge, and using our current, we should be able to find the amount of time it takes. All right, so the amount of carbon dioxide is going to equal 6.05 e neg 3 mole. Okay. And then if we go back, the carbon dioxide, it'll be 2, it's basically the ratio is 2 carbon dioxides per 12 electrons. So the amount of, there will be 6 times as many electrons as carbon dioxides. All right, 6.05 e neg 3 times 6 is going to equal 0.0363 mole of electrons. Now the charge is going to equal the amount of electrons times F. So it's going to equal 0.0363 times 96,500. 96,500, which is 3,502.95 coulombs is our unit. We know that Q equals IT, so therefore T is going to equal Q divided by I, which is going to equal 3,502.95 divided by our effective current, which is 1.566, which is 2,236.88. Now that's in seconds. The question does ask in minutes, so we're going to convert that. We're going to say 2236.88 divided by 60, which is the amount of seconds in a minute, is going to equal 37.3 minutes. And our values that we've measured here are the 3, so I'll leave it as 3 significant figures. All right, so that's that one. Let's do a couple more. A current of 8.65 amps is passed through a 0.5 liter aqueous solution of 3 molar copper nitrate. No electrodes used. How long will it take? So we're looking for a time value. Will it take for all the copper to deposit at the cathode? So we have a current value, a volume value, and a concentration value. So you might be looking here and you go, well, I've got current, but I don't have time and I don't have charge. So how do I convert between anything? We also don't have amount of electrons, amount of our copper, or our mass of copper. What we can find though is we can find the amount here. So we have a volume and we have a concentration, so we can find an amount. So an amount of copper, that's going to be 2 plus, is going to equal 3 times 0.5. So concentration times our volume, which is going to equal 1.5 mole. All right, so we can find our amount of electrons from there. We know the amount of electrons is there's going to be 2 electrons per copper. So that's going to equal 1.5 times 2. Okay, that's just going to go back to 3 again. And then we can say Q is going to equal 3 times 96,500 equals 289,500 coulombs. And then we can, again, we can do the same thing as last time and go T equals Q divided by I is going to equal 289,500 divided by 8.65 divided by 8.65 is going to equal 33,468 seconds. Now we can see that they've got the answer in amount here. Sorry, the answer in amount. We can see they've got the answer in hours. So we'll do 33,468 divided by 3,600, which is going to give us 9.3 hours, which is going to look an awful lot like this one here. We can see they've also done it to 2 significant figures. I don't think that's actually correct. This isn't a VCAL one. This is 1 significant figure, so we would round it to that. All right, let's keep going. We've got 500 ml solution of a metal salt with 2 inert electrodes. A current of 3 amps is applied for 1 hour and 1.9 gram of metal is deposited on the cathode. 500 ml solution used in this electrolysis cell is, all right, so we've got kind of 2 values here. We've got a different variance in concentration and we've got variance in the, well, the different masses and the different charges basically. So this is kind of like the one before where we had to trial and error it. All right, so what we can find straight away, we have current and we have time, so we should be able to find charge. So charge is going to be equal to I2, which is going to equal 3 times 3,600, which is the amount of seconds in 1 hour. 3 times 3,600 is 10,800 coulombs. All right, and if we have that, we can find that the amount of electrons is going to be equal to 10,800 divided by 96,500. Oops. Minus 6,500 is going to be 0.1 0.112 mole. Okay, so there's that many electrons. And we've kind of got a few different possibilities here. So we've got copper, silver, or chromium. If we're looking at copper, we're looking at half that amount because it's 2 plus copper. So it's going to be 0.056 mole. If we're looking at silver, this is going to be the same amount. So it's going to be 0.112 mole. And if we're looking at chromium, it's 3 plus. So it's going to be 0.112 divided by 3, which is going to be 0.0373 mole. All right, so now that we've got the mole here, we can find the amount of each of these. So we've got 1.9 grams, and we can compare what the amount of each of these would actually be. So we've got 1.9 grams. So for copper, this would be, let's have a look here, copper 63.5. And it's going to be 1.9 divided by 63.5. Which is going to be 0.03 mole. Okay. Our next one's going to be silver. Silver, and we could look it up. I'm just going to say 107.9 because we did it earlier. 1.9 divided by 107.9 is going to be 0.0176 mole. And finally, we have chromium, which is going to be 1.9 again, divided by mass of chromium is 52. And it's going to be 0.0365. So out of the three of these, the closest one seems to be the chromium here. This silver's pretty far off. The copper's pretty far off. Chromium's pretty similar. So I go with D here. One thing to note is that the concentration of the solution shouldn't actually matter here. That only matters if all of it's been plated on. So this should be basically, that's kind of a clue that it's not A or B here. All right, so I think that's enough examples there. So hopefully you've got an idea of how to use those different equations. Basically, it's just using the same equations, figuring out where you are in that kind of like linear string of different conversions that you can do, and figuring out which direction to go. Follow it to where you need to go, and you'll be fine from there. All right, let me know if you guys have any questions. And other than that, I will see you later.